As you've seen and you will continue to see, scikit-learn has a lot of machine learning models, has a lot of tools and functions that we require when we are working on a machine learning problem. And I encourage you to spend some time and look at the scikit-learn website. You can see how it's broken down between the classifiers, the regressors, clustering models, dimensional reduction, model selection, pre-processing. You can go ahead and look at all the models, all the tools that scikit-learn has to offer you. It's a rather mature package that is well documented, so I encourage you to get familiar with the website, take a look at it, see what additional models you have. And of course, we'll be discussing some of the key models and how to use them and how to get the best performance out of them as we go throughout the course. Of course, we cannot talk about everything involved with scikit-learn, but the documentation is there. But the point I want to make here is that, of course, scikit-learn cannot provide you everything you need for the problem you're working on. Of course, there might be some tools, some models that they just don't have because your problem might be too specific or something like that, or perhaps it hasn't been developed just yet. But the nice thing about scikit-learn is that it's going to offer you a way for you to extend scikit-learn's functionality, particularly in the realm of creating your own custom estimators. This is often going to be the case where you have a data set that needs some sort of pre-processing. Data is found in so many different formats and so many different ways it's configured that there's just different ways we want to work with the data to get into the right format to pass it down to some other machine learning model, specifically some sort of predictor to make predictions on. For example, we can sketch this out using a process diagram. We have a data set. It's coming in right there. We got to apply some sort of transformation to this data to get into the right format, a very nice format for a downstream model. So there needs to be some sort of pre-processing that needs to go on here, some sort of transformation process before we feed it into a predictor. So we can define some sort of unit, some sort of process to do this transformation in our data. But it'd be nice that if we can go ahead and have that code that we construct, that model we construct, that estimator we construct, have it work well with the infrastructure of scikit-learn, with the environment of scikit-learn. It'd be very nice because if this custom estimator we construct that we are going to create for our problem, if it is compatible with scikit-learn, then we can use other tools of scikit-learn, things like pipelines. Hopefully you've been convinced the power of pipelines, the importance of pipelines. Pipelines are necessary, or not said necessary, but are very useful when you have a workflow of more than one step. Of course, if you only have one step, there's no need to use a pipeline, but oftentimes you have multiple steps to go from the raw data to a trained model. You should use pipelines. So any custom step we create, it'd be very nice if we can just erase it there. If we can go ahead and encapsulate it using pipelines. So whatever we create, we want to make sure it's 100% compatible with scikit-learn. And we can do that with scikit-learn. As we've seen with scikit-learn, scikit-learn is going to heavily rely on object-oriented programming principles for these machine learning models, for these transformers, for these predictors, these regressors and classifiers. These models are going to exhibit itself as classes. That's how they're programmed. Classes. We construct objects from those classes, and once we have those objects, we can go ahead and fit them, and then once they're fitted, we can call transform if it's a transformer, or call predict if it's a predictor. So scikit-learn is going to allow us to create our own custom estimators. And the way it works programmatically is that we're going to exploit the concept of inheritance. Inheritance in object-oriented programming principles is the idea of creating a class that's derived from some sort of base class. So there's no need to reinvent the wheel. There might be some previous class that defines some basic functionality. We inherit from that class, and then we add the additional functionality that defines this custom class we're creating at the idiosyncrasies of the new class. We'll see this example. So we'll see an example for this section of the lecture. Now, let's say we have a data set And in this data set, there are perhaps rather extreme values of the features. And we understand that these extreme values of the features might prevent our model from working well. So let me just go ahead and sketch that out. So let's say I have a distribution. This is my distribution. This is the value of one of my features, x of 1, and let's say this is how my distribution looks like. Distributions of x1 values. But I want to do some processing of my data set. I want to remove, I don't want to necessarily remove, but I want to modify some of those extreme values. So what I can do is I can say, in this region of my distribution represents the 5 most extreme points on one end, the high extreme. But we also have low extremes. So let's say this cutoff represents the other extreme 5%, such that what remains in our data set is 90% inside this better behaved region. So what I want to do with my model, with some transformer I want to create, I want to take points that reside above this marker, above this point, take those values and truncate their value. For example, if this cutoff exists, let's say at 7.5, all values greater than 7.5 get reduced to 7.5, are going to get pushed to exist within this ceiling for this feature. Very similar thing I want to do for the lower extreme. Let's say this cutoff exists at 0.3. So values less than 0.3 are going to exist in this 5% region. So all those values that are less than 0.3, I want to keep those points, I just want to modify their value. I want to push them upwards such that if I have a value, let's say 0.1, let's set it equal to 0.3. Push those extreme values on either end up to their floor, up to the floor, up to the ceiling, so such that I can modify the following distribution. That's the task at hand. I want to create a tool, an analysis to do this pre-processing on my data set. But I want to do it all in the infrastructure of scikit-learn. I want to create a transformer that can work well with the other tools of scikit-learn. Specifically, so I can put it in a pipeline. I want to still use all the other tools afforded to me of scikit-learn. I want to make a custom transformer such that scikit-learn is going to see this model and it's going to think it's like any other transform it has built in. So that's the task at hand. Let's go about programming this custom transformer so we get an idea how we can go and extend scikit-learn with additional tools we can create for our specific problems and analysis. I'm going to call this model Outlier Replacer. Notice I'm going to take advantage of the camel case convention. So the first letter of each word is capitalized. So I say class, the name of my class, Outlier Replacer. It's not removing outliers, it's simply replacing their values. Keep that in mind. The first class is going to inherit is the base estimator. All estimators are going to inherit from this base class. Think of it as the skeleton scaffolding for our custom transformer. Got to inherit from the base estimator. Now, what type of estimator do we want in this problem? We want a transformer. So it's going to inherit a second class. It's going to inherit a second class. In this case, this class is the transformer mixin. So this is the class that's going to define this estimator specifically as a transformer. There are other ones that can inherit. We'll see those in a bit, but that's the one we are working on. We want a transformer, so we'll have it as a transformer. Okay. So for this, the first method we're going to define in our class is the init method. The init method of a class defines what are the attributes we want to define for an object when we create an object from the class. In this case, we want some flexibility for the user. We want the user to define where should these cutoffs be in terms of percentages. In this figure here, what I had the lower cutoff being 5%, so the lower 5%, but also want to cut off values that are greater than 95% of the points. So I have two cutoffs, the lower cutoff and the higher cutoff. So in this example here, if you're below 5%, those are the ones I'm going to modify the values, but also if it's greater than 95%. But it's also be nice if the user can modify these values. Perhaps I want something that is not as that is more lenient. Maybe perhaps I want to have my cutoffs located elsewhere. Maybe this represents only 1%. This region and this really small region also represents 1%. I know things aren't drawn to scale, so just believe me here. In that case, the cutoffs will be less than 1%. The values that are less than 1% of everything else, and those that are greater than 99% of the values. So that's a different cutoff, and I want to have that user to have that control, right? Let's make it general as possible. Let's make this class as general as possible. So that's going to manifest itself by these two attributes, Q lower and Q upper. Remember how the first argument of a method is self? Self is a strong convention in Python. It's going to refer to the object itself. So we're saying the object has an attribute called QLower, which is equal to QLower passed by when you created the object. Same thing with QUpper. Okay, we define the init method. The next method we need to define for our custom transformer is the fit method. Now in the fit method, here goes the code, the calculations that are required to perform the transformation. So this is where this goes. This is sort of the gut, the main part of the method, of the class. So for this example, I need to figure out what is the value of my feature that represents these cutoffs. Is this 5% cutoff? Is it located at 7.5? Or is it located at 7? Is it located at 8? Where is the location of this cutoff? In other words, what is the feature value that represents these two cutoffs, the lower extreme and the higher extreme? I need to figure out where these cutoffs are. That's what needs to occur during the fit method, because if I know those cutoffs, if I know where those cutoffs occur in my distribution, then I can use that to modify my data set, to apply the transformation. This is something I need to know for my transformer. Anything that I need to know and calculate for my transformer, that's going to go into the fit method of my transformer. So a nice way we're going to figure out these cutoff points is by using the percentile function in NumPy. So let's go ahead and we can look at the code for that function, NP percentile. Take advantage of being able to look up the documentation in scikit-learn or any other packages we are using. Like I said before, it's impossible to memorize how exactly all these functions work all the time. These change as they update to different as you update the versions. Hopefully not too drastically, but just be comfortable enough you can open up the documentation and understand how it works. So if you look at here, it says compute the qth percentile of a data along the specified axis. This is exactly what we want to do. And of course, there's some examples later on, shows you the usage of this function. But what we'll want to do is pass a data set and say, figure out where is that cutoff. We want to figure out where is that the location of the cutoff, and that's where this percentile function will tell us. So we use the percentile function. We pass the data set. I should back up. Let's look at the signature of this method. In other words, this first line here. The first parameter is self. Don't forget about that. It's a common mistake. Then we're going to pass the data set. We pass the data we're going to use to fit the transformer. And since this transformer is not going to use any labels, we say y equals none. So don't forget to include this part of the method definition. Y equals none if you're not using the labels for the fit process. No need to use labels here. We set y equals none. All right. So we say, okay, figure out the location of the cutoff of this data set using Q upper and Q lower. And the values that we calculate that come out of this function, we want to store them in attributes called upper and lower. Why would we want to store these values? Why would we want to store these values as an attribute for any transformer object, this transformer object, any objects we create from this outlier replacer class? Why do we want to store these values? We want to store these values because we're going to make use of them when we transform our data set. We want to make use of them, so we want to store them as attributes such that when we get to the transform method, when we define what is the transform method for this transformer, we make use of Q lower and Q upper, of upper and lower, these upper and lower values that we calculate during the fit method. As I said before, what goes in the fit method? In the fit method are going to go into calculating any parameters, any coefficients, anything needed for the transformation process. And all the stuff that we need for the transformation process, they should be stored as attributes of the object. So that's exactly what we do here. One thing I want to point out, you might be wondering, what is this axis equals 0 argument? If we go into, let me just sketch out our data set. This is going to appear a lot when you're working with NumPy. Let's say we're working with a two-dimensional array, a matrix, rows and columns. If we want to specify, so in this case, we want to figure out what is these cutoffs for all the features of my data set. So I have x1, x2, and x3, and so forth, all the way to x of p. However many columns we have, how many features we have in our data set. We got to do this process for all the features. The distribution I showed you before, that was just a sample distribution for one feature. We got to repeat it for all the features. So we got to figure out these cutoffs for all the features in our data set. So when we apply the percentile function, we want it to be applied down the rows. Because if we apply it down the rows, we're calculating a single value for each column. Since we are calculating this operation down the rows, in order for you to tell NumPy that's what you want to do, you have to set the keyword argument axis equal to 0. Because the axis 0 is the row axis. Rows are 0, columns are referred to as 1. If we wanted to do it by a different dimension, let's say across the columns, calculate some value across the columns, to get a single value for each row, you would say axis equal to 1, since you're performing it across the columns. In this case, we're doing it across the row, down the rows, we say axis equal to 0. You need to specify that when we do this operation. If you don't specify what axis, it does it for the entire matrix. We don't want that. We don't want a single value for the entire matrix. You want a single value for upper and lower for each column, for each feature. Hence why we got to set axis equal to 0. I want to make sure I point it out so it won't be too confusing. All right. When we're creating our custom transformers or any custom estimator, the fit method must return self, which is going to be a copy of the fitted estimator. I want to make sure return self. If you don't return self, if you try to use this in a pipeline or anything like that, you'll get some sort of error message saying about none doesn't have this type of thing. You'll get some messages about none in your error message if you forget to return self. So return self is going to return a reference to the estimator. So let's actually play around with this. Let's go ahead and run this code here, run this block. So we define our transformer with the init method and the fit method. So we just it doesn't have the transform method, but that's perfectly fine. Let's go ahead and we'll flesh that out in a bit. But let's play around with this whole return self thing. I know it can be a bit confusing when you first see it, when you're creating your own custom estimators, why you need it. Okay, so with what we have now, let's create a object of our outlier replacer. So we set the cutoff as, the lower cutoff as 5% and the higher cutoff as 95%. So we pass those two arguments when we create the object. Let's call fit. Now sometimes when you're doing this, when you're working with these models, you would do something like this. You would just do replacer equals the outlier replacer, and you do replacer.fit, and you pass x. You would do something like this. So notice in this situation, it looks like replacer, typo there. Oftentimes you would not assign the output of the fit method to some variable, to some name. You just simply have it because it's going to modify that object in place. But if you wanted to, you could have assigned the result, the return value of the fit, to some new name. In this case, we reference it to replacer underscore copy. And I want to prove to you that this name is going to refer to in memory the same object as replacer. We can do that by using the is statement. Replacer is replacer copy. This is going to return true if these two variables point to the same object in memory. Or we can do the comparison, we can do the check by looking at their ID. The ID function will give you I believe it gives you the memory address of the object. So if they're the same, then hey, these two variable names, even though they're different variable names, they point to the same object in memory. So this should return true on both instances, and indeed they return true. So replacer copy and replacer are the same thing. So modifying one will modify the other. Just want to point out that when you do the fit, you can assign the result of fit to a new variable name if you so want to, but you don't have to. Oftentimes you'll see the syntax that we have above and we've seen so far in the course. We'll be using the course. Create the object, create the estimator, estimator.fit, pass the data, and we don't assign the result of the fit method to anything. Okay, make sure we clarify that. So the last thing we got to do for this object, for this class, this custom class we're creating, we have to define the transform method. What does it mean to transform the data set? So let's define that transform. Notice in the transform method, the first argument is self, and the second argument is x. So there's no y's being passed. We're going to just transform the data set. First thing we were going to do is we're going to make a copy of the past data set. And this is helpful because we want to make sure that during the transformation process, we don't modify the original data set. We don't want that to happen. That might cause problems, especially if you don't know what's going on inside this transformer. It might have some unintended consequences for other processes that are going outside of your workflow of this transformer. So we make a copy of the data set. And then one thing we got to do is we got to figure out what values do we need to replace. What values are within this extreme region, the lower and upper extreme. So if I go back here, if I sketch it out once more, so this is my distribution. So I have something like this. I want to figure out, and now I figured out during the fit method where these cutoffs exist. But now I got to figure out what points are within this extreme region, this outer regions that are defined as extreme. I can do that using NumPy, using some operations with my NumPy arrays. So I say x is less than self-lower, self.lower. Notice we're making use of those stored attributes that we created, that we figured out during the fit method. So x underscore self.lower will return all the indices where the x values are lower than the cutoff. So those are the ones I want to modify. So I've identified those and I stored those in the int lower variable. Now let's do it for the upper extreme. What indices of my data set have extreme values on the other end? So x greater than self.upper, I identified those values. Those indices where those values occur. Now what I got to do is I'm going to loop through all the columns of my data set. That's where I go through this for loop for I in range of x.shape -1. So the number of columns, number of features in my data set. Then I go about replacing those extreme values. That's what this code does here. It's figuring out all the values in my data set that exist in these two regions and replacing it with this cutoff point. In other words, if this cutoff point is 7.5 and I have a value at 8, it's going to truncate it to 7.5. Same thing with the extreme. If this extreme value, this cutoff is 0.3, any point that is less than 0.3 is going to get replaced to be equal to 0.3. So we're going to truncate those values, apply a hard ceiling and floor to my data set. So I apply the transformation, and I'm assigning it to my x of t, the copy of my data set. And that's what I end up returning in my transform method. Okay. Let me run that. So I defined my outlier replacer, define all the methods that are required. Let's go about using it. Let's go about using our custom transformer. Let's see how well it works. So I'm going to create a variable called replacer. So I have my replacer object, set the cutoff at 5 and 95. Let's fit the replacer. Let's call transform on the replacer. So I'm going to assign that result to x of t. So now x of t represents my modified data set. Let's go ahead and look at the distributions, right? Let's compare the distributions. Let's see, in fact, whether it did what we wanted to do. So how should you expect our plot to look like? So let's say this is our original distribution. What do you anticipate our histogram of the transform data set to look like? What do you guys think? How would it look like? So essentially what our transformer is doing, it's taking these extreme values and then pushing them to this cutoff. It's taking these extreme values and it's pushing them to this cutoff. With a probability distribution function, we have a, quote, conservation of mass. The area under the curve must be equal to 1. So you can think of, we're pushing this mass that exists in the extremes, we're pushing it to the floor and the ceiling. So there's going to be a spike near these cutoff points. So that's what we anticipate how it's going to look like. Let's go ahead and look at the histogram for our 0 feature. Right, we can do this for all our, I believe, 7 features in our data set, but let's just look at index 0, so column 0. Let's look at the original distribution, and let's look at the transform distribution. So notice in blue, so we have our distribution. It's got a tail on one end. But after the transformation, this mass here got pushed up. These masses here got pushed up, so that's why you have those spikes at the very end. So we've applied our transformation. We replace those extreme values with the floor and ceiling. Okay. And that should be, yeah, so that's all I want to say regarding custom transformers. So we'll discuss in a bit creating custom regressors.